It's a pleasure for me to introduce Professor Mikaël Attal from the School of Geosciences at Edinburgh University. So his research focuses on how landscapes evolve, particularly the links between tectonics, erosion and river systems. He uses field data, modelling and experiments to explore how sediment moves through rivers and what this means for hazards like landslides and flooding. And he'll be talking to us today about a sediment's grains journey from source to sink. So please may you all welcome Mikaël.
It's a pleasure also to be here, despite the fact that I'm not here in person. I've never been to Hull, but it looks like a great place to do research on rivers at the moment. And so thank you for the invitation. And what I'm going to do today is I'm going to take you on a journey from thinking about sediment grains and thinking about where they start, where they go, what we can learn from them, and also the sort of problems associated with the production, transport, and deposition of sediment. There's also so this is sort of this is based on like more than 20 years of work that I've done, starting from my PhD to work I've done with colleagues, PhD students, colleagues over the years. And so this is definitely not just my work, it's a team effort. And yeah, let's start. So sediment grains, like the ones we saw on the previous pictures, like we can see them everywhere. Everyone has seen a pebble. Everyone has taken a pebbles in their hand, put them in their garden, skimmed them. They're everywhere, but we tend to sometimes underestimate how much information, how much knowledge can be gained from these grains. So, for example, like pebbles, they are the tools for erosion. So when you're in a landscape that's made of bedrock, most of the time, nothing happens to these landscapes, but when rivers start flooding, you will have these grains are going to start being transported, impact the bedrock, and cause some erosion. They also, the sediment grains, they are the witness of past events in the geological history of the Earth. These are conglomerates from the island of Kerala. I think they are Devonian in age, if I remember well, and you can see here these beautiful sedimentary features with this gravel. So we had rivers that were transporting sediment from the now eroded Caledonian orogeny, which was on the size of the size comparable to the Himalaya. And if you go to Scotland, you wouldn't know it was there 300 million years ago, but they're still the remnants of that big mountain range. And what other best example than Sika Point, which is considered one of the most important geological exposure on Earth. This is the place where James Hutton took people and introduced them to the idea of the Earth being a bit older than 6,000 years old. And his idea there was that you had rocks that were vertically bedded here, which we knew at the time were deposited at the bottom of the ocean. So they had to be deposited horizontally. They had to be turned into rocks. They had to be put to the vertical. And then on top of that, you can see there's a valley that has been carved into this sediment. And then in this valley, you can see river sediment with some pebbles, some clasts that have been detached from the underlying ground and reincorporated into this sediment. So very huge, very high amount of information contained in sedimentary structure. Sediment grains, they are also a resource. So when we talk about pebbles, you can extract gravel for all sorts of building. You can build houses, you can build roads, but they're also hazards. So when sediment gets released rapidly during some catastrophic event that we will talk about later, you can have these sort of things happening to whole cities, and the consequence can be catastrophic. So what we're going to talk about also, I'm going to also mention, for most of my research, I've talked about gravel, but there's also sand has become more important as I was looking into the transport and production of sediment. So in terms of resource, what you can see, sand has made the headlines in the past few years because sand is a very important construction material as well. And in places, in particular in Asia, where there's construction boom and there's a lot of sand, you can have unregulated mining that causes problem. Like we can talk about the India's sand mafia. There's been articles by Chris Hackney and colleagues who have looked at the impact of mining on river like the Mekong, for example. You know, the world is running out of sand and we need to do something about it. And this is just an example that they published where they showed how sand mining over the course of 7 years completely changed the morphology of this river here in Bangladesh. So all these pock marks are places where sediment has been removed, and over a few years the river got much deeper. And when you have a river that's getting deeper, flow velocity is greater, and you end up with problems like bank erosion, for example. Linked to that as well, deltas are becoming very susceptible to climate change as well, because we have rising sea levels, but deltas are also strongly dependent on sediment coming from upstream that keep replenishing the land. So it's a constant battle, and it's the trade-off between sediment coming from upstream and rising sea level. So if you stop the sediment coming from upstream because of dams or because of sand extraction, you're making these areas even more susceptible to climate change. And it's not just an Asia problem, like it's a problem that we can see all over the world, including Florida here. That was an article that was published a few years ago. So what I'm going to talk about as well in this presentation is I'm going to talk about where is sand coming from, and I'm going to talk about the importance of sediment grain size on channel morphology and dynamics. So that's the structure. We're going to follow the sediment grain journey. We're going to talk about sediment production, where the sediment grains start their journey. We're going to talk about abrasion. So in these very simple diagrams, I've illustrated what happens when you've got mountains. So in the mountains, sediment is produced. It gets into the river, get transported by the rivers out of the mountains, and typically you will have sediment being deposited downstream. So we're going to talk about the sediment production. We're going to talk about abrasion, what happens to these sediment grains as they are being transported. We're going to talk about this trade-off between gravel and sand and where sand is coming from. And then we will talk about sediment-driven hazards and maybe some perspectives if we have the time, okay? So the first thing that I want to talk about is about sediment supply. And one of the things to think about sediment supply is that it tends to be episodic. Things will go quite rapid. You will have rapid events that are going to supply sediment into the river. And we will talk about that when we will talk about the sediment-related hazards, but it's also spatially variable. So what are the spatial variations that we're thinking about? Well, they're mostly driven by changes in sediment source. And Leonard Sklar and colleagues in 2016 came up with that nice diagrams, which I think exemplifies what's happening to sediment grains and how that can influence the type of sediment that we find in the river. So sediment will be produced from bedrock that is fractured, grain starts being detached, but what is going to come out of the river will depend on the path that this sediment grain take from their source to the river on the hill slopes. So grain that come straight from the rock will have a different grain size to grains that spend some time into what we call the weathering engine. So the idea is that as grains spend time into the soil, into the saprolite, they have time to be broken down, and the grain size distribution is going to be affected by that. And they presented that sort of conceptual model here, where we have a sort of initial bedrock grain size here. So D is the grain size in millimeters, so it's a logarithmic scale. And here, this is, you find on the x-axis, the sediment grain size. So they have this curve saying, let's imagine that what's coming from the bedrock has this distribution. And here on the y-axis, we've got the particle size supplies to the channel. So we transform that distribution depending on how much time spent in the soil is going to affect this distribution. We may end up with something that looks smaller in size compared to the original grain size. So this is, I'm not going to go into the details of explaining this diagram, but 2 points here is that based on the initial distribution, you can sort of predict what will be supplied to the river. In that case, we've got 50% soil, 50% outcrop. But also the second point that I want to make is this is a hypothetical curve. And we have very little information about grain size of sediment sources. So that's something that I worked on during my PhD. I worked on during my postdoc as well, and I'm also going to present a few studies to show the impact that changing sediment sources can have. And what I'm going to present here is three broad types of sediment sources that are related to the environment where sediment is being produced. We can have glacially derived sediment, like here in the Marcandi River in the Himalaya. In low relief soil mantle landscape, you will have different types of sediment as well. Grains are going to spend time in the soil, and the soil is going to creep to the river. And then we've got the steep landscapes that will be dominated by rockfall and landslides. So the first place we're going to go is the Feather River in California. And here we have the Feather River here that is incised into a low relief landscape. And if you look at that, you can see that catchments do start on the plateau, and then there's a break in slope. The rivers get steeper, and then they join the gorge, the canyon where the main river is flowing. So there's a wave of incision that's propagating into this plateau, and very big change between the grain size here and here. And what we wanted to do is see how the steepness of the landscape, which we can relate it to the erosion rate, like the landscape that's steeper is going to erode faster than the landscape that's less steep, is going to influence the grain size distribution of the sediment in different places. So we've got this schematic diagram, and we took sample up here on the low relief landscape, down here where the river started incising and where relief starts growing, and then in the places that are sort of adjusted, that were very steep and had both soils and landslide. What we have in this diagram, this is showing you the grain size, and we've got two grain size, there are two percentile. So we've got the median grain size, the D50, and we've got the D84, which is the 84th percentile. It's the coarse fraction. That it's a measure that we use to characterize the coarse fraction. And we have that for the soil, and we have that for the landslide. So a couple of observations. The first one is not totally surprising, but we've got data to characterize that. There's not much data out there. Is that, well, landslides are going to supply sediment that's much coarser than soil. And we're talking about that as we get at a gradient above around 0.7, you can see that we start having landslides, and their median grain size here is like 2 orders of magnitude greater than the grain size of the soils in equivalent as steep landscape. But even within the soil, we can see differences. You can see that as we double the slope from here to here, the median grain size of the soil goes again up by an order of magnitude from 0.1 to 1 millimeter. So the steepness of the landscape, the rate at which you erode the landscape, is influencing the grain size of the sediment coming from the river to the channel. There was another study that I think was really nice as well. And what I like about this work is, so that's work by Odin Mark and colleagues in Taiwan here. And what they looked at is a series of sites, and they measured the grain size of landslides in a series of locations that had different rock types and different characteristics. So again, these pictures really illustrate why it's difficult to get grain size distribution for this sort of sites. It's varying a lot vertically, it's varying a lot laterally, and some of the grains are the size of whole cars. So, it's very hard to constrain that. But they did, and they tried to, what I liked about this work is that they tried to come up with some ways of quantifying the sort of grain size in relation to other measures that could potentially help develop some models. So here, for example, they showed that as the drop height, so that's the height between where the landslide started and where the landslide ended here. So there is a sort of the median grain size here. As the drop height increased, the median grain size seems to decrease, but it's not a very, very strong correlation. However, what they did, they used two models here that they try to calibrate and validate. And the first one is a model by Cohen et al. That shows the median grain size of the hill slope, the D50, as a function of the depth into the hill slope. So as you go deeper, the sediment is getting coarser. So the red is a model, the white is their data. So there's a sort of, they managed to calibrate that. But based on this relationship, then they started looking at the relationship between two parameters. The first one is a reduction ratio. It's the initial grain size of the sediment before the landslide occurred, divided by the median grain size of the sediment in the landslide. So actually it's the opposite of a reduction. Well, the greater it is, the greater the reduction, okay? And here they've quantified the ratio of potential energy to the strength of the rock. And we got a very nice relationship here based on this equation by Mikaël Attal in 2006. So what I like about this sort of work is that then suddenly we have things that we can quantify that can help us predict the sort of grain size that we will have into our hillsides, into our hill slopes. Why does that matter? Well, the source is, this is where our grains start, and like very basic observation, the coarser the sediment you put in the river, the coarser the sediment in the river. Here we have some data to exemplify that. That's along the Marsandi River, which is in the Himalaya. And what we have here is as we move downstream, we go from a place where most of the sediment is glacially derived. And here we've got the grain size again, showing the median grain size in blue of the subsurface, in red of the surface. And when we go from places where sediment is glacially derived, like rivers are incising into till, the moment we get into the gorge of the Marsandi River in the high Himalaya, we have suddenly a big increase in the grain size, and that's associated with a change in source. This is where landslides start providing sediment to the river. Another example to support that is an example from the Apennines now in Italy. We've got a Cilano Gorge, we've got a fault here that is uplifting that block. Again, we're going downstream here. We've got the grain size. The dark blue is the median grain size. The light blue is the D84. And what we can see is that the river starts on a plateau again. We've got soil mantle landscape, quite small grain size. And as we arrive at that point, there is a gorge that starts occurring, slopes get steeper, and again, an order of magnitude increase in grain size. And the moment we get out of the gorge, the grain size decreases again. So the grain size of the source is having an impact on the grain size of the sediment you find in the river. So that's for our first part. Now our sediment is in the river. What happens to it as it moves downstream? You've probably all know that grains get abraded. The rivers are going to transport the grains. They're going to hit each other. They're going to change shape and size. So typically, the grains are going to start, the grains that get into the river, they tend to be quite angular. There's going to be quite a poor sorting where you start. And then there's a series of abrasion processes that are going to transform these grains. So typically you can have chipping that is going to remove all the sharp edges. Grains can be crushed between larger grains. Cracking is a process by which, through multiple impact, you're going to propagate cracks, which eventually will coalesce and detach a grain. And you can have grinding as well, where depending on the angle at which the pebble impact each other, they may detach fragments. Splitting is the sort of extreme version of cracking, where the cracks have propagated through the wall pebbles, and you crack your pebble into 2 or 3 large pieces that suddenly become really angular. So these processes, all of them reduce the size of the pebbles. Most of them tend to then make them more rounded. This is the only one that can take a round pebble and make it angular. So we start here and we end up with that, okay? So do we get downstream fining? We've all heard about downstream fining in our geography courses. Do we get that in mountain rivers? Well, if we're in mountain rivers, no, because as the sediment from here is being abraded and transported downstream, there's fresh sediment that's coming all along the course from tributaries, from other landslides that can prevent this downstream fining. Something that could reveal difference in abrasion rate, though, is looking at the different rock types and whether they change in proportion in the sediment. The idea is as such. Let's imagine that we start in A and we've got 2 rock types, a pink one and an orange one, and these grains are being transported downstream. If the 2 rocks are eroded at the same rate, the 2 grains are going to reduce in size at the same rate. If you look at the fraction of the different grain, it's not going to change. So if we started at 50% pink and 50% orange in A, we will get 50% pink and 15% orange in B because they are reduced in size at the same rate. If the pink rock is more resistant than the orange, then the orange is going to reduce in size faster than the pink. So when you look at the gravel here and you look at the percent mass between the two, you're going to see that the pink is going to be become more abundant than the orange when you look at the fraction in mass. So what we did, so that was my PhD. I built a big flume, a big washing machine, and we put pebbles in that flume, and we tried to look. We tried to understand the impact of a series of parameters, but I'm just going to show just the impact of having different rock types on how quickly the grains abrade. So you can see this is the pebble abrasion rate in % per kilometer, and it's a logarithmic scale. So the quartzite is the hardest rock, around 0.1, 0.2% per kilometer. You get volcanics, you've got granite, gneiss, limestone. And what was interesting is that for this, like the rates were comparable to other studies. But what we did in that flume, we were trying to replicate the conditions, the transport conditions that are prevalent in big Himalayan rivers. So we had a flow velocity of up to 4 meters per second. And what we showed is that actually sandstone and schist, depending on the degree of cementation or how fissile the schist was, you could get abrasion rate in excess of 10% per kilometer due to the grains just breaking very rapidly in this case. So up to a factor 200 between the strongest rock and the weakest rock here. So that's from the experimental data. And so we also surveyed the gravel along the Marciandi River to try to see if we could see these differences in the rock types. So the advantage of the Marciandi River is that it's incising along all its course, so we can remove like selective transport as part of the equation. And what is nice also is that we've got different domains that have very different dominant lithologies. We're in the Tetian series up there, it's mostly limestone and schist. Here in pink, it's the gneiss and the granite from the higher Himalayan crystalline. And then as we get into the lesser Himalaya, it's mostly schist and sandstone down here. And what we have here is the % area of different lithologies as a function of distance from source. So you can see that if we start at 40, if we start up here, like most of the catchment is made of 60% limestone, 10% quartzite, 10% sandstone, 20% schist. And as we move downstream, this proportion change. So here, for example, at 50 kilometers, the gneiss and the granite starts appearing. And as we come out of the outlet of the river, we have the contributing area is made of 20% limestone, 10% quartzite, 10% sandstone, 30% schist, and 30% gneiss. So if all these rock types were being abraded at the same rate, you would expect that the gravel in the river would show the same proportion. But instead, that's what we find. And like you will see, like two very clear observations here is that, well, it's highly variable. But more importantly, like the resistant rock types, like the quartzite, the gneiss, and the granite, so the yellow and the pink, end up completely overrepresented with respect to the poorly resistant rock types, like the schist and the sandstone. So the schist and the sandstone can make up 50% of the catchment here, but they never represent more than 10% of the gravel that you find in the river. On the other hand, quartzite, that never represent more than 10% of the rocks exposed in the catchment, represents 60% of the rocks exposed when we get near the outlet. So we see that in a lot of rivers. We've got the Red Deer River in Canada that showed that over a distance of 500 kilometers, quartz and granite become the dominant rock type. And Mezaki and Yabiku in 1984 looked at the Kali-Gandaki River, which is parallel to the Marciandi, and they made similar observation. It's a very similar diagram to what I've just shown you in the Marciandi. Downstream is to the left, but again, as you move downstream, you start here with the limestone and the quartzite, and as you move downstream, the gneiss and the granite appear, and then further downstream, the quartzite become dominant. Okay. So after a few hundreds of kilometers of transport, quartz becomes the dominant rock type in the gravel. So in summary, we start with angular pebbles up in the headwaters. We've got a varied rock type. The pebbles are abraded during the fluvial transport, and you will end up with pebbles that are more rounded and the resistant rock type dominant. So what happens to all the other rock types? What has happened to them? Like they didn't disappear. Well, they produce a lot of sand. So the product of abrasion is going to be a lot of sand. And how much? Well, that's what we're going to look at in the next part of this presentation. So gravel versus sand. To illustrate this trade-off between the two, we are going to the Himalaya again. And this is work that Lizzie Dingle and Laura Quick in particular have been doing. And the idea is that if we summarize the Himalaya, we've got two plates converging towards each other. The Indian plate is being pushed down under the Asian plate. The mountains are rising here. Mountains get eroded, sediment gets transported, and sediment gets deposited in the flexural basin here. This is the Ganga plain in northern India. What we see also is that as we, let's look first at how deep that Ganga, that flexural basin is. So what I'm looking at when I'm going to show you on the next slide is the depth under the surface of that contact here. So that's the underlying plane. And the depth to basement, you can see that it decreases as you move towards the south. We've got the Himalaya here, we've got India here, and the basement is at around 8 kilometers under the surface here. So all that has been filled up with sediment. What happens to the gravel when it comes out of the mountains? Well, what we observe is when you're up in the mountains, you have big rivers transporting very large grains. So this is here along the Kosi River. We've got Emma Graff and Laura Quick here, and our driver here who was very helpful in the field. And this is a gravel bar. These grains are, like some of them are a meter in diameter. These get transported during big floods during the monsoon. So sediment is coarse, is being transported by these rivers. And as you come out of the mountain front, you see a very rapid reduction in grain size. Okay, so here we're a few kilometers from the mountain front, and the grains are much smaller. This is not abrasion, it's too fast to be abrasion. So the idea is that actually you come out of the mountains, the river lose power, and they just deposit all the gravel. And you exhaust the gravel over a given distance. So here that was us doing the surveys, like people were very curious about what we were doing here. And yeah, very quickly the gravel disappears over the course. Like we have here what we call this gravel sand transition, and the moment you pass that over a course of a few kilometers, the rivers are just sand. It's just sand everywhere. You barely see any gravel. So all the gravels get trapped upstream of that gravel sand transition. So what is interesting is that Lizzie Dingle tried to map that gravel sand transition at the front of the Himalaya, and she found that it was between 45 kilometers from the mountain front in the Yamuna to only 10 kilometers from the mountain front in the Kosi River. However, like Duby and Lave a few years before had published a paper looking at these rivers here, small rivers just feeding the Himalaya here. You can see the catchments. There are these little dots here. This is a zoom, and you can see these are the tiny catchments that we're looking at. And this is where they found the gravel sand transition along these rivers. What puzzled us is that that distance was very similar to what we found along the main river. This is the Kosi River. This is the largest catchment. Sorry, this is the largest catchment in Nepal. And the gravel gets exhausted over 10 kilometers, and it's the same on this small river. So what Lizzie did, she did a calculation about how much gravel can we get an estimate of the gravel flux based on the geometry of the fans and the location of the gravel sand transition. So she made this calculation, and for the Bakeya, which is this small catchment here with the gravel sand transition here, she calculated, so it's a catchment that's 350 kilometers square, and we get a gravel flux of 500,000 tons per year. The Kosi catchment, which is 50,000 square kilometers, more than 100 times bigger, the gravel flux is nearly 1 million tons per year, just over double the gravel flux. And what we found is that abrasion could explain these differences. So what we have here on this map, let me have a quick drink. Okay, what we have on these maps here, the colors represent the percent of gravel supplied. So we imagine that we've got the catchment, we've got the Bakeya here, which is 30 kilometers long here. And we imagine that each pixel is going to provide some gravel to the river. This gravel is going to be transported, and the color tells you how much of the gravel that has been supplied by this pixel is still gravel when it comes at the outlet of the Bakaya River. So if you're close to the outlet, everything is gravel. The further away you are, and the more of the gravel has been abraded. And so here, for example, this is for a mass loss of around 2% per kilometer, which is what we found in your flume for gneiss and limestone, for example. So you can see that in the Bakaya, even when you're in the headwater, like up to 70% of the gravel that's supplied here remains gravel when you get to the outlet. However, when you look at the Kosi, which is on a very different scale here, that's 300 kilometers, okay? And what we can see is that like the further away and the less likely you are to find gravel that comes from that far away. Like everything that's in the red means that essentially all the gravel that's been supplied here, by the time it makes it to the outlet, there's no more gravel left. Everything has been abraded and turned into sand. And here, what I've shown here is I've put the Bakaya to scale to match with the Kosi. And that explains why, despite the fact that the big difference in size between these two catchments, like there's not much more gravel coming from the Kosi, because most of the gravel is going to come from here, from close to the outlet. And the idea is that increasing a catchment size above a given value is not going to lead to much more gravel because everything coming from upstream will be abraded away. So the idea is that these two rivers provide almost very comparable amount of gravel, but the Kosi River will provide much more sand in that case, because all the sediment coming from here would have been turned into sand by the time it comes out. So in summary, this is a sort of conceptual diagram to show that dichotomy between gravel and sand. So what you will find in terms of deposition, we've got the main frontal thrust here. This is the Himalaya growing here. And this is the Ganga plain. This is where sediment gets deposited. And what you can see here is that all the gravel is going to be trapped upstream between the gravel-sand transition and the mountain front. So all the gravel will be trapped here in green, and most of the gravel will come from an area that's quite close to the outlet, like typically around 100 kilometers. However, that's very different from sand that will come from all over the catchment and will be much more mobile. It's going to be deposited over the floodplain all the way to the Bengal fan. All right. So for the next part, I want to talk about sediment-driven hazards. And again, there will be some elements of what we've just talked about that will come into this sediment-driven hazard part. So when we think about sediment-driven hazards, we think typically about landslides. That's when a lot of sediment is coming down into a river in one go. And these pictures from the Hokkaido earthquake in 2018, I think, are very spectacular. They show how, following the earthquake, wall hillsides came down and completely filled up the river. It's going to take some time for that river to process that sediment and evacuate it. That was the Wenchuan earthquake in 2008 as well. Incredible pictures again showing landslides and walled cities completely buried into sediment, up to like 10, 20 meters of sediment at that point. So close to the place where the landslide, the sediment is being supplied, the impact is very visible and can be catastrophic. It's not just earthquakes that are going to cause sudden release of sediment. That was the Carabelada debris flow in 1999. So we're in Venezuela here. And we had a very heavy rainfall. And what happened is that following this very heavy rainfall event, you can see the hillsides upstream of that catchment. We're looking upstream and you can see the hillsides. There's been a series of landslides that just came out at the same time. And unfortunately, in many places in the world, people tend to build in flat areas. And these flat areas sometimes are alluvial fans, so it looks like everything is fine. But when there is an extreme event, the rivers do what they do on alluvial fans. They transport sediment and they deposit sediment. So that city was almost obliterated, with the damage being on a scale that's really incredible. Look at the size of this boulder on the second floor of this building. Wall houses have been completely buried in this event. So extreme rainfall event can cause that as well. And closer to home, so that's 60 kilometers from where I grew up. This is Saint-Martin-Vésubie in the Alps, just near Nice. And I used to go there, very pretty village, very alpine, pretty village, typical village. And in 2020, this place experienced one of these events again. And so when we talk about precipitation exceeding half a meter per day, like 20 years ago, that would have been like unimaginable. But these days, we have a handful of these events happening somewhere in the world. So for Saint-Martin-Vésubie, what that meant is this. So over the course of a few hours, this big flood came down. And again, you can see it's coming from different tributaries and it completely obliterated the valleys. What does it look like when you're in the field? This is what it looks like. You know, the carving that has occurred, the sediment transport is on a scale you would have not imagined. If you had been there, I had been there, I would have never imagined an event like that would have been possible. But one of the things that you notice when you start looking at that, one of the cause of this event, and that's a theme that you're going to see for the rest of the talk, is you realize that actually the whole landscape, like there's the bedrock, but there was a lot of sediment in the valley. The whole valley was built on sediment. This is post-glacial sediment. So we were in the mountains when the glacier receded. So a lot of that sediment is sitting there. And when you go up in the headwater, so this is Saint-Martin-Vésubie here, and when you go up in the headwater, you see that everywhere. A lot of sediment has been transported. The grain size is extraordinary. This was a year after the event, by the way, and you could still see the impact. I heard that actually they're really struggling to stabilize that because essentially what you can tell is that the whole landscape is with sediment plastered everywhere in the landscape, glacial sediment. And what this event caused, it caused the undermining of these hill slopes, and it's going to be nearly impossible to stabilize that. So this event, they're rare, they mobilize a lot of sediment, and they have impact that are going to last for some time. This is something that we've seen in Nepal as well. That's a paper that Emma Graf published last year, where we're talking about the Melamchi disaster. So different scale here as well. So we went there, like Emma was looking at the dispersal of sediment following the Gorkha earthquake, because typically when you've got a big earthquake, you get a lot of landslides. Sediment gets in the river, rivers start transporting this sediment, and you can see the rivers changing shape, depositing a lot of sediment in places, eroding in other places. And what Emma found is that actually nothing really happened to the rivers after the Gorkha earthquake in 2015. For some reason, the landslides did not lead to a big pulse of sediment in the river. What did, on the other hand, was an event in 2021. So let's talk about this event. This was us surveying this river. So you can see the Melamchi River here. This is Melamchi Bazaar, lovely town. This is the Hotel Roach here. And we put the total station here. You can see that they had put embankments, thinking, okay, if there's some flooding, we put this embankment to protect the river. That's the bridge here. That's the embankment. And after, this is a picture from before the event. So that's that footbridge that we can see here is here. The Hotel Roach is here. And that was after the event. That junction here is that junction here. The Hotel Roach here is there. It's buried in sediment all the way up to here. So there's only the top floor that's coming, that's sitting out. There's a river now flowing. There's a branch of the river that's flowing here. And a lot of buildings have disappeared. There's the bridge, the road bridge is gone, the footbridge is gone. And this is just to show you the extent of the damage. So we're looking downstream now. And from the viewpoint is from here, we're looking downstream. That little house here is that house here. So essentially that event, the Melamchi disaster, filled up that valley up to 10 meters of sediment. That's a bit of the bridge here. And that was a catastrophic event that came from a series of events led to that disaster. Let's look at where that came from. And I think this was the interesting, one of the very interesting results, is that we thought, okay, there's been a big rainfall event. like it looks like suddenly the landslides from the Gorka earthquake had an impact on sediment transport. But when we look at the satellite imagery, we found something surprising. So we've got the Melamchi Valley down here. Okay, this is where the sediment came from. This was before the event in October 2022. There's the Yangri Valley down here. We will talk about that in a minute. And in orange here, we've got the co-seismic landslides. These were the landslide from the 2015 earthquake. And this is the picture after the event, after the Melamchi disaster. And what you can see is that most of the sediment, if we map the extent of where the sediment came from, and we can see that in the Yangri Valley as well, this is where the sediment starting from. It started much further upstream than where the landslides are created. All the sediment has been sourced from these valleys that were glacial valleys, when glaciers retreated, and they left piles of sediment behind. More importantly, a large part of the sediment came from that thing, the Bremtang area, where we recognized that afterwards, when you look at satellite imagery, essentially we have this was a landslide dam that's maybe thousands of years old, we don't know. And behind this dam, there is this braided section where the dam was there and the river has accumulated sediment, so potentially hundreds of meters of sediment in this valley. And what happened during this event, which we think now may have started from an outburst flood here, what happened is that when the flood came down, it breached that dam that has been stable for years, and all the sediment that was stored behind that dam just started moving. And it started moving. You can see there's a gorge incision here, so that's the incision into the landslide dam. And then all the sediment behind started being put in motion. That's just to illustrate that point again. We're zooming now. This was the landslide dam here. This was this braided section here. And this is what it looks like now. So you can see in the river profile, you can see this landslide dam, the Melamchi, this is the one we're talking about. And you can see this valley that had filled up with sediment. And after breaching the dam, the sediment got transported and flooded, completely buried Melamchi Valley further downstream. In the Yangri Valley, that's just to the east, it looks like there's another one as well. Again, you can see when you zoom in that area, you can see what looks like a dam, like a river is coming down and filling up with the valley with sediment. And when you look at the river profile, again, you can see this low gradient valley. So Kristen Cook started talking about this as landslide, as sediment bombs. There are places up in the headwaters of valleys where there's just a lot of sediment that's been there, that has been stable potentially for decades, hundreds of years, but changes in climate now are making this sediment being mobilizable again. So potentially comes a big event, all that sediment can come down and represent a huge hazard for these places. And the world changing hydrology is really something maybe not as extreme as what we've just talked about, but even like this year in September 2024, okay, 2024 was last year, but in September 2024, Kathmandu experienced like very heavy rainfall, never recorded, up to 320 millimeters in 24 hours. And what you can see is that part of the city got completely buried in sediment. Saraswati Thapa, our PhD student Saraswati Thapa, was working in these valleys, and she was looking at specifically this river. So this is the brand new hospital, and what you may see here is a series of embankments, like these sinuous lines. They are embankments. The river, the Naku River, is just a tiny river that used to flow there, and she was looking at the impact of sediment flux and caliber on the flood risk of this area, and also looking at the impact of this constructed embankment. And she showed how actually this embankment may do the job for a small magnitude event, but comes a big magnitude event, they will just not be able to stop neither the water nor the sediment. And unfortunately, these events are becoming more frequent, and we can see that happening underway. So that was Kristen Cook, who wrote that News and Views following this event. Okay. I'm going to spend maybe just the next 5 minutes talking about the implication further downstream. because we're looking now, like all this example that I've talked about, we're in the mountains, you know, where the sediment is coming down, the areas that are next to this mountainous area are affected most. But what happens further downstream? So what we're going to do now, and that was part of Lizzie Dinger's PhD, we're going to start looking at what's happening further downstream. So what we have here, like based on the abrasion work, what we found is that well, we were worried about the impact of the Gorka earthquake. If you've got the Gorka earthquake, you get a lot of landslides, a lot of sediment, and that sediment is going to be transported downstream. And the thing is that when you're in the mountains, you know, you deposit sediment, a few meters of sediment, it doesn't have a big impact. But if you're further in the plain, it can have a big impact because you've got a low relief area. And what came out of that is that actually, following the Gorka earthquake, we're not going to see a pulse of gravel in the plains or in the Ganga plain, because based on the distance during the Gorka earthquake, most of the landslide occurred up in the high areas of the Himalaya. By the time this sediment is going to be transported to the floodplain, it will have been turned into sand. So we expect a pulse of sand in the floodplain. However, if we have an earthquake, a very big earthquake that moves the main frontal thrust, if we have an earthquake that shakes the areas very close to the mountain front, then we expect to have a lot of gravel coming into the river and making its way into the floodplain. So what came out of the work with the abrasion is that depending on how far you are from the landsliding area, you may witness a pulse of gravel or a pulse of sand. And that's going to have an impact on how the river is going to respond to that. Because if you start depositing sand, it may not be as long lasting as if you start depositing gravel, for example, which can have an impact on flood risk. So in the low-lying area, if you deposit gravel, you're going to change the flood risk quite significantly. This is work that, for example, Maggie Creed and Lizzie Dingle and Saraswati Thapa were involved in trying to model the impact of just changing the riverbed elevation by a couple of meters along the Karnali River. So the Karnali River, we will go to the Karnali River in a minute, but what we have is the river coming out here. It goes into two branches, and this is modeling the flood risk for a flood that has a recurrence interval of 20 years. We have the cities here. This is 10 kilometers. We have the border with India is just here. And what you can see is that if you raise, so this would be with a given riverbed. On the left, the riverbed is raised by 1.8 meters. And you can see there's some differences. There are places where it doesn't make a big difference, but places where it does. And in particular, the area around downstream of Tikapur, like the patches of flood that you could see here start being connected, and the flooding is much worse, for example, in this area. So just a couple of meters of sediment aggradation can completely change your flood risk. So there is the flood risk, but it's like depending on whether you transport gravel or sand, you're going to also influence the river dynamics. And that was something that is based on some work we did in 2016. We went down the Karnali River. So again, the Karnali River is here in western Nepal. The river comes out in Chizapani, separates into two branches, and then connects again. It's a very weird river, but very interesting and very beautiful place as well. We've got the mountain front here, and the gravel sand transition is around here. So what we did, we took a boat and we tried to sample. We were trying to understand how much sediment was being transported during the monsoon. So that's the boat that Ed Tipper lent us. We have here a cross section. So we did an ADCP survey, acoustic Doppler current profiler surveys across the river to get an idea of the flow depth and the flow velocity. So here, this is just upstream of the mountain front in Chizapani, and we can see flow velocities in excess of 3 meters per second and flow depth of around 7 meters. So it's a deep, like the discharge was very high at that place. But what we did also, we did sample sediment. So this is what the work looked like. And So we had to take the boat, go upstream of the point we wanted to sample, and then we turn off the engine. When we get to the point that we want to sample, we've got Lizzie is going to drop very carefully the thing. Hugh Sinclair here on the left is going to start pumping to trigger the sampler, the valves of the sampler. And we did that again and again and again and sampled at different depths. So here is our nice sample. We can take samples at different depths. And yeah, this is that little video that I showed you. That's how far we traveled. So it did take a bit of time to get these samples, between 5 and 8 samples at every location. But what we found is the following. So what we have here is the data. We've got the normalized depth on the left-hand side. So this is the bottom, this is the top. And we've got this different location. T1 is in black, it's the further upstream. Then we've got T2, T3, T4, and T5 is the one that's downstream of the gravel sand transition. So what we found is that here we've got the grain size. So we can see that as we move downstream, the grain size doesn't change much along the profile. So everything is well mixed. And the grain size goes down as you move downstream to T4. And then when you get to T5, the grain size there's a big gradient with very coarse sand being transported at the bottom of the river. In terms of the sediment concentration, this is a logarithmic scale here. And that was really stunning as well, because from T1 to T4, the concentration doesn't change. Again, it's well mixed, but they're also very similar. But then you get to T5 and you have a huge concentration near the bottom of the channel, like a lot of sediment, very coarse sediment, a lot of it is in suspension at the bottom of the channel. And when you make the calculations of the flux based on this data, you can see that as you move downstream from T1 to T4, you've got pretty much constant flux. And then you get to T5, as you pass the gravel sand transition, the sediment flux increase massively. So where is this extra sand coming from? And the answer came from that. So this is T5, this is where we surveyed. And over the course of the survey, which was a couple of hours, that bank moved by around 5 meters. As we were there, there's around like 6 meter depth here, and you could hear the bank. The banks are eroding, and plof, 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 you could see the bank progressively being eroded away. So because we are downstream of the gravel sand transition, these banks, they're just made of sand. The floodplain is just sand and silt. And when you look at the satellite imagery downstream of the gravel sand transition, this is what you see over the course of a few decades. The rivers are changing rapidly on a yearly basis. So over the course of a few years, the river can migrate by kilometers. And that's just because the banks are made of sand. They are not very strong. And as a result, a lot of the sand that we measure in the river, a lot of the suspended sediment in the river is coming from bank erosion rather than coming from upstream, which we think is a very important result, in particular when you're taking sediment, looking at provenance or using cosmogenic nuclides to get erosion rate. So on a yearly time scale, you've got rapid lateral migration. On the other hand, if you go upstream and you look at the upstream of the gravel sand transition, you can see that over like the same period, the river has barely changed its course. And that's because when you have a stable channel, and when you go there, you can see that actually these are not embankments, these are natural gravel levees, and it's much harder for the river to move when the banks are made of gravel. However, I mean, we know this is an alluvial fan, so we know that the rivers are moving. And actually, when you look at the satellite imagery, you can see old channels there. So we were thinking about how can we tell how frequently the rivers are changing. So these are the old channels, and Lizzie and Laura and Hugh went there and they sampled these channels for OSL. And the dates that they found are these sort of dates: 850, 490, 2500, 1500, 4000. So it looks like upstream of the gravel sand transition, the channel is stable, but over like a few hundreds to a few thousand year time scale, the channel is going to move rapidly from one place, from one place to another. And that's probably driven by avulsion and extreme events. So essentially, the river is doing nothing for potentially hundreds of years, and then a big event occurs and the river shifts completely its course. And so I think because of the time, I'm just going to finish with that slide. And that was a sort of summary that illustrates how this trade-off between gravel and sand can influence the sediment flux, can influence the dynamics of the rivers as well. And in particular, in the example of the Himalaya, but there's other places where you've got gravel sand transition. Upstream of the gravel sand transition, you will have stable channels, and the rivers are going to change dramatically their course by avulsion, as for example the Kosi avulsion in 2008 that you may have heard about, when the river moved its course by 20 kilometers following a breach of its levee. But downstream of the gravel sand transition, you will have rivers that are migrating much more rapidly, and a lot of sediment being recycled from that process. And yeah, I think I'm going to stop here so that we have the time to take any question. Thank you for your attention.